Hello everybody, this is Dr. Schleith, and in this video I'll be going over the learning objectives related to momentum. As usual, please keep a record of all of your work in a physics journal. Take pictures of every page of your journal and send me scanned copies of your journal is my preference. If you can scan that all as one PDF and send it to my email with your self-evaluation somewhere in the body of the email out of 100 points, and make sure that you turn that in by noon Friday each week. All right. Because we are going to be defining linear momentum, this should be pretty straightforward. State and apply the principle of conservation of momentum to collisions in 1 and 2 dimensions, relate force to the rate of change of momentum, and discuss energy changes in perfectly elastic and inelastic collisions. We'll first define linear momentum. Linear momentum is a vector quantity. It's equal to the product of mass and velocity. It's measured in kilogram meters per second, so kilograms of mass times meters per second of velocity. And we could kind of think about momentum as a measure of the difficulty in stopping a moving object. Here I have two examples. One is something that has a lot of momentum. So like a meteor flying through space has both a lot of mass and usually pretty high velocity. So that would be something that has both high mass and velocity, a lot of momentum, very difficult to stop. A helium balloon isn't very massive and doesn't really travel that fast, and so that would be something with not a lot of momentum. A stationary object is not moving, has a velocity of 0, and therefore has no momentum, but may still have mass. State and apply the principle of conservation of momentum to collisions in 1 and 2 dimensions. So first we need a statement of the principle of conservation of momentum, and momentum is one of those quantities in physics which is conserved, and so there are sort of three great conservation laws in physics. There's the conservation of mass energy, the conservation of linear momentum, and then the conservation of angular momentum. Here we're focusing on linear momentum, and one way to think about it is within a closed system, the total momentum in any direction is constant. That is, we can add up the individual momenta of all of the particles, and it's going to add up to a constant. We could also say that for a closed system, in any direction, the total momentum of the objects before the collision is equal to the total momentum of the objects after the collision. So you sum all of the objects' momenta, and that's the total momentum on sort of one side of the equation, initial, before the collision, and then you sum all the momenta of all the particles to get the total momentum of the particles or objects after the collision. That's sort of another side of the equation, and that's always going to be equal for any closed system. And note that there's sort of that qualifying statement in the first one too, within a closed system, and that's one where there's no sort of outside forces acting. State and apply the principle of conservation of momentum to collisions in 1 and 2 dimensions. And so here we have an example of trolley A of mass 0.8 kilograms traveling at a velocity of 3 meters per second, collides head-on with a stationary trolley B. Trolley B has twice the mass of trolley A. The trolleys stick together and have a common velocity of 1 meter per second after the collision. Show that momentum is conserved in this collision. The way that you would approach this calculation is to determine the momentum of trolley A. Because it has mass and it has velocity, we take the product of 0.8 kilograms and 3 meters per second. 0.8 times 3, right, is 2.4 kilogram meters per second of momentum. Because they collide and they stick together, this is an example of what we'll describe as an inelastic collision, one that's not bouncy, so it's inelastic. So we can kind of think about the final momentum as now there's like one new object that's equal in mass to the sum of the individual masses. And it tells us that trolley B has twice the mass of trolley A. So if there are 2.4 kilogram meters per second of individual momenta, let's take a quick note of that. So P is the letter we use to represent momentum in physics. So the initial momentum equals the final momentum. Here's a way to sort of think about the law of conservation of momentum. And we've already calculated that the initial momentum all comes from trolley A because trolley B is stationary. So while it has mass, it has no velocity and therefore it doesn't contribute to the initial momentum of the system. All the momentum comes from trolley A, So 0.8 kilograms of mass times 3 meters per second is 2.8 kilogram meters per second of initial momentum. Now, the final momentum is going to be something that has the mass of trolley B plus trolley A. Trolley B has a mass of 1.6 kilograms because that's twice the mass of trolley A, which is 0.8 kilograms. So if we add 1.6 and 0.8, we realize that our object has a final mass of 2.4 kilograms. And because they tell us that this new object is traveling at a velocity of 1 meter per second, you can kind of think about multiplying 2.4 kilograms times 1 meter per second is 2.4 kilogram meters per second of final momentum. And so we've shown that the initial momentum equals the final momentum. We'll look at other examples of inelastic collisions and how we can think about approaching different collisions in terms of, do they stick or do they bounce? Elastic and inelastic collisions, which is the subject of another learning objective. Here's another example related to the learning objective: state and apply the principle of conservation of momentum to collisions in 1 and 2 dimensions. It says one sphere of mass 0.5 kilograms moves to the right at 2 meters per second. A second sphere of equal mass moves to the left at 3 meters per second. The two spheres collide, and after the collision, the first sphere is moving left at 2 meters per second, and the second sphere is moving right at 1 meter per second. Prove if this is possible using the principle of conservation of momentum. Here, I'll leave it to you to kind of work through this one on your own, and I'll just give you a piece of helpful advice that remember that velocity is a vector, and so you need to use a sign convention and make one direction negative relative to the other one because we have spheres that are moving, both left and right. So just make sure that you stick with the convention that you choose, whether right is positive and left is negative or whatever you decide, but be consistent in your calculation. And then leave it in the comments down below. This language comes from the ACE Physics syllabus, so it is in the syllabus and it's posted online. Apply the principle of conservation of momentum to solve simple problems, including elastic and inelastic interactions between two bodies in one dimension. And it says that the knowledge of the concept of coefficient of restitution is not required. Relate force to the rate of change of momentum. That's one of the learning objectives. And so we actually define force as the rate of change of momentum. This definition leads to impulse momentum theorem. So we could think about force as being the change in momentum over the change in time. So remember, that's like the final momentum minus the initial momentum. If we were to multiply both sides of this equation by the change in time, by delta t, then we get a term on the right that we call impulse. Force times the change in time is impulse. And impulse equals the change in momentum. And that's what we call impulse momentum theorem. Impulse equals the change in momentum, where impulse is just this product over here, force and time. Discuss energy changes in perfectly elastic and inelastic collisions. In perfectly elastic collisions, kinetic energy is conserved. So we sort of define a perfectly elastic collision as one in which the kinetic energy of the particles or objects involved in the collision is conserved. So there's no kinetic energy loss. So it's like a perfectly bouncy collision where they just bounce off and they keep all of the kinetic energy. There's no energy losses. That's sort of idealized motion. In fact, in kinetic molecular theory, it is one of the assumptions that gas particles collide with perfect elasticity. But most collisions are going to be somewhat inelastic. That is, when objects collide, usually there is kinetic energy lost, and the kinetic energy of the object is transformed into other forms of energy, which might go into deforming the materials that are sort of involved in the collision, or heat or sound energy, something like that. So usually some kinetic energy is converted into other forms. although momentum is always, always conserved. In fact, there is nothing into which momentum can be converted. So the law of conservation of momentum is sometimes a little bit more straightforward than the law of conservation of mass energy because kind of as the name suggests, the law of conservation of mass energy, well, that just kind of goes to show you that energy and matter are kind of two sides of the same coin, and energy can exist in all sorts of different forms, including as mass. But there's nothing into which momentum can be converted. And so the law of conservation of momentum, we can sort of always track the momentum that's there initially, has to be there finally. There's nothing into which we're converting that. But kinetic energy can be converted into other forms of energy. If it's not, if all the kinetic energy initially equals all the kinetic energy afterwards in a collision, then that collision is what we define as perfectly elastic. And that's what this learning objective is about. In inelastic collisions, some or all of the kinetic energy is converted to other forms. As I said, like heat and sound would be examples. Most collisions are inelastic, as we mentioned. Kinetic energy is converted into other forms. And the syllabus language says, show an understanding that while momentum of a system is always conserved in interactions between bodies, some change in kinetic energy usually takes place. When it doesn't, when the kinetic energy is conserved, that's when it's a perfectly elastic collision. But most collisions, indeed, are inelastic. So with elastic collisions, kinetic energy is conserved, and that leads to really a helpful realization here. And in the syllabus, it says, recognize that for a perfectly elastic collision, the relative speed of approach is equal to the relative speed of separation. And this is sort of like how two objects see each other. So the relative speed of approach will equal the relative speed of separation because the kinetic energy is conserved. Mathematically, we could kind of think about it like this, where u1 and u2 are the initial velocities of the objects, and v1 and v2 are the final velocities of two objects, 1 and 2. We'll derive this equation, the relative speed of approach equals the relative speed of separation, from the law of conservation of momentum and the law of conservation of energy, which we'll also put to good use for this week's lab work with the ballistic pendulum. So click on the link to see the derivation of this. Once we derive it, we can just kind of use this. It's often easier to approach a problem where we either know that kinetic energy is conserved, and so we can kind of use this to say, oh, this is a perfectly elastic collision. The speeds of approach will equal the relative speed of separation. Or sometimes we may be trying to show if a collision is indeed elastic or inelastic, and we can kind of use this fact that if we can show that this is true, then the collision must be perfectly elastic. So how do we calculate the relative speed if we're saying that the relative speed of approach equals the relative speed of separation? What does that mean, and how do we calculate the relative speed? So if objects are traveling in the same direction, then you're going to subtract their speeds to find the relative speed. So just kind of imagine two cars moving in the same direction along a road, and one might be going, say, 55 miles an hour, and the other one's only going 50 miles an hour. Because they're going in the same direction, how do those cars sort of see each other? Well, one car sees the other car sort of moving 5 miles an hour faster, or the other one sees it moving 5 miles an hour slower, relatively speaking. If those objects are moving in opposite directions, though, we're going to add their speeds to find relative speed. And so this would be an example of two cars passing each other, sort of on the interstate, each one going 70 miles an hour, and each car would see the other car is going, 140 miles per hour, because each one is, speeding towards the other one at 70 miles per hour. Or 70 meters per second, if you will, in physics class. So you kind of want to ask yourself, for calculating relative speed, how do the objects see each other? And mathematically speaking, that's going to sort of boil down to, if they're going in the same direction, subtract their speeds to find the relative speed. If they're moving in opposite directions, add their speeds to find the relative speed. And for a perfectly elastic collision, the relative speed of approach will equal the relative speed of separation before and after the collision. As I mentioned earlier, our lab day this week will be the ballistic pendulum, and we're going to use the law of conservation of energy and the law of conservation of momentum to determine the initial velocity of a projectile fired into a stationary target of known mass, suspended from a string. And this is what we call the ballistic pendulum. So I'll go through all of the explanation and working so that we'll be able to reach a claim, which is going to be what is the initial velocity of our projectile. So the claim that we're going to reach is the initial velocity of the projectile is. And this week we're actually just going to collect a single good data point to really just practice with the calculations with these laws. We're not going to do a full-blown experiment where we're going to vary one quantity against another one, but just kind of look at collecting a single data point, and then maybe we'll revisit this lab and looking to see how we might improve upon it to get a stronger experiment. Be sure to check the links to this video for both a more detailed explanation of the lab work as well as the derivation of the perfectly elastic idea that the relative speed of approach equals the relative speed of separation. That's really a consequence of the fact that kinetic energy, by definition, is conserved in a perfectly elastic collision.